Good morning, everyone. My name is Urmish, and I'm the engineering manager within the NLP group at Sambanova Systems. Today, I'm very excited to talk to you about the software and hardware innovations that we have used to build a new class of deep learning training system. So, before I dive deeper into the talk, I wanted to take a detour and then talk about astronomy a bit. Specifically, I want to talk about the Goldilocks zone. So from an astronomy point of view, Earth lives in a zone which is sort of deemed as the Goldilocks zone. The reason this zone is so important is that if you're a little closer to the sun from where we are right now, it becomes too hot for life to survive. And if you're even slightly away from where we are right now, it becomes too cold for life to survive. The reason I'm taking this detour is to sort of create an imagery to sort of convey that when it comes to deep learning model architectures, we are living within this Goldilocks zone. While Goldilocks zone earlier was advantageous for us, in this case, I would argue that this is kind of detrimental for us. Models that adhere well to the programming model that GPU provides and the architectural limitations that it provides are the ones that get adopted really quickly. But models that are slightly away from where GPUs has its strengths would not get adopted that quickly. These kind of models will run quite slowly on GPUs, and it will be very hard for researchers and production engineers to iterate over them and productize them quickly. A very valid question to ask is that, do we even care about these kind of models that don't really map well onto a GPU? And my answer to that question is going to be yes. So if you look at the Goldilocks zone that the GPU has locked in, there are models on the left-hand side and the models on the right-hand side. The models on the left-hand side are more to do with productizing deep learning applications and installing them in a latency-sensitive scenario or in case of an always-on application. These are your tiny BERT models or deeper and skinnier models that give you good ISO accuracy on a niche application, but require far less compute than the larger applications that they are distilled from. On the right-hand side of the curve are these extremely giant large language models, which have gone into trillions of parameters. These large language models are really, really interesting because they enable a new paradigm way of interacting with machine learning application that was not previously possible. As someone who is not ML friendly or ML savvy, you can interact with these large language models using a natural language interface, provide very few labeled samples, and suddenly you can turn these large language models into state-of-the-art solutions that you can deploy. This can enable any enterprise customer to become a state-of-the-art AI vendor without having to understand too much about deep learning. But both of these classes of application that lie on the left-hand side and right-hand side of the curve that we saw previously are really hard to run on a GPU. On the left-hand side, even though you have sort of less number of flops, you don't see the significant speed advantage that you would expect from these models for the amount of flop reduction that you see. And on the right-hand side, you really need to be a systems engineer expert to run these extremely large language models on farm of GPUs. So this Goldilocks zone that GPUs have created is not something that we have discovered. A lot of different vendors that you see here, some no longer exist now, have tried to sort of unlock and sort of allow people to develop new models that are outside these Goldilocks zones. We believe that Sambanova system is uniquely positioned to unlock this Goldilocks zone and create a deep learning computing system that can accelerate the full model spectrum. And the way we sort of break out of this Goldilocks zone is by fundamentally innovating across all layers of the stack. Specifically, we look at models and look at all the layers of the stack with which it interacts with our deep learning system and have innovated across all of these layers to develop a new training system that we are shipping to our customers, where customers are able to run all different kinds of application at a remarkable performance. So I'll take an end-to-end approach in this talk. I'll sort of dive deeper into innovations at each layer of the stack, and then sort of finish it off with talking about application innovations that we have done by using the hardware-software stack that we have created. All right, so let's dive deeper. Now, at the heart of the Samba Nova system architecture is the Reconfigurable Dataflow Unit, or RDU. RDU is an architecture designed for spatial computing. From a primitives point of view, you can think of a RDU having a compute unit, a memory unit, and an interconnect fabric. Now, we looked at different deep learning applications and looked at the compute and the memory operations that execute on them, and have broken them down into what we call as parallel patterns or primitives that you use to program an RDU. And using these primitives, you could enable all different kinds of deep learning algorithms that you care about. These primitives will end up landing on either a PMU or a PCU or an interconnect unit and allow you to express complex nodes that you see in your application. For example, some primitives would require a single, some nodes will require a single primitive, but a more complex node like softmax might require multiple primitives to enable things like exponential, reduction, and then subsequent division operation. Now let's try to understand why having this kind of a spatial architecture that is developed for data flow computing is advantageous. To understand that, let's look at what happens on a GPU. Suppose you have a deep learning graph, and that deep learning graph has multiple operations. These would be multiplication, normalization, softmax. The way you will execute this on a GPU is using a kernel by kernel execution method. First, you'll execute the first op, then the second op, then the third op, and so on. Now, the reason this kernel by kernel execution method is inefficient, because for each op that you execute, you need to pay a lot of cost. These costs are with respect to the kernel launch latency, to configure your GPU to run that particular operation. Then once you have configured the GPU to run that operation, you need to read in the values that the op requires from your memory. These could be your wait values, your activation values, anything that is needed. Finally, once you are done executing, you need to store these values back into the memory so that your next op can use it. RDUs execute graphs in a fundamentally different way. We have heard a lot about data flow graphs, and this is what RDUs are designed for. In case of RDUs, you map the entire graph simultaneously onto the hardware and ensure that none of these latencies or op launch costs that you are paying, you need to pay now. Overall, this eliminates overhead and maximizes utilization. So let's take a concrete example. In this case, you see a convolutional neural network with two convolution layers, a pooling layer, and a summation layer, a normalization layer and a summation layer. We use the primitives, the parallel patterns that we talked about to configure the RDU to express this graph and laid it out spatially. The primitives have configured the graph to mimic the data flow that you see in the original deep learning application. Specifically, you see the convolution layers feeding into the pooling layer, feeding into the next convolution layer, and so on. Now, when you have laid out the graph this way, data flow execution becomes extremely easy. You take a single batch, break that batch into possibly multiple samples, and feed that particular batch one sample at a time. When the first layer is done executing on the first sample, it will pass on the output to the next layer and will simultaneously start executing the next sample in the batch. In a way, you have created pipeline parallelism that maximizes throughput, but you have also ensured that the outputs are never written back to the memory. The output of the first layer will always feed into the output of the next layer, creating that producer-consumer paradigm. Overall, what this means is that you are not paying a kernel op latency or launch latency. You are not paying the cost of going back to the memory to reading something from the memory, and you're not paying the cost of writing back to the memory also. And this overall allows us to achieve higher performance and higher throughput than what we see on a GPU. Now, sort of laying down a graph onto an RDU is a non-trivial amount of work. In this case, we rely heavily on our compilers to figure out the optimized way of executing this graph onto our Dataflow chip. The compiler is extremely important because an inefficiently designed compiler can create a graph on a chip that is extremely inefficient to execute. In this case, you are looking at a complex deep learning graph that you generally see in the kind of solutions that we ship to our enterprise customers. And if you had a poor compiler, you would see the producer-consumer nodes laying at very different ends of the chip, and then you need to allocate a lot of amount of buffers to transport data from one node to the other node. However, if the compiler is designed well, you can turn this deep learning graph and map it in a more simplistic manner and achieve the kind of performance that I have been talking about. So to understand what this hardware architecture allows us to do, we have tried to map the programmability versus the energy efficiency of this architecture. So in this graph, you see the energy efficiency on the y-axis and the programmability on the x-axis. And if you look at it, the RDU enables us to achieve the same energy efficiency of a fixed function accelerator without having to sacrifice the programmability of what you achieve on a CPU and a GPU. A valid question to ask then is, where does FPGA lie in this context? And from an FPGA point of view, we achieve far better flexibility than what an FPGA can allow us to do. So we talked a bit about what the architecture is, what is unique about the architecture, and how it's suited for the deep learning graphs that we see, for the Dataflow graphs that we see in our deep learning applications. Now let's look at some of the algorithmic innovations that we have done to complement our hardware and also enable our hardware to push its limit. Specifically, I want to talk about a pure 16-bit training regime. So low precision training is something that has existed or people have tried to pursue as a research endeavor for a very long time. And you have seen some amount of success. There is always going to be a paper that will talk about a data set, a model architecture, and sort of prove that low precision training works for that particular data set and for that particular model architectures. Sometimes they will target a bunch of architectures within a single domain like computer vision or NLP. However, a lot of these training methodologies do not really scale well. In the end, when you want to productize something, you need a technique that works generally well, not isolated for a specific data set or a particular application. And for a lot of these low precision training methodologies, what we see is that if you tweak the data set a bit, if you tweak the architecture a bit, the claims kind of fall apart, and you need to get into extreme amount of hyperparameter tuning to get back to the claims that were previously achieved. Yet, this is something that's really important because low precision training can help you achieve higher system efficiency with possibly with minimal accuracy impact. And the reason it achieves higher system efficiency is because if you have a compute unit that's specifically designed only for low precision training, specifically, if you have a compute unit that's designed only for 16-bit training and does not even care about 32-bit training, you can do a lot from a design point of view in the sense that you can decrease your chip area by 1.5x, you could improve your energy efficiency by 3x, and you could increase your throughput by 1.5x. And if you achieve these goals, you can use these gains to pack more compute, they possibly pack more memory, or whatever you want to do, sort of to trade off the gains that you have made. I talked about all the research that have happened in low precision training, and I talked about some of the issues that these trainings have. The way people have sort of mitigated this issue is to move away from low precision training and do what is called as mixed precision training. In case of mixed precision training, there's a part of your graph that gets executed at lower precision, but your weights are still always stored at a higher precision. What that means is that you do get some amount of compute benefit of low precision training during your forward and backward propagation. But from a hardware point of view, your compute units still need to support the high precision compute because your weights are in 32-bit. So when you do your optimizer step, you would end up using those particular paths in your hardware. So all of the gains that I talked about in the previous slide are actually not being achieved from a hardware point of view. So the question that we asked ourselves is that, can we only support 16-bit training on accelerators while achieving the same accuracy as 32-bit training? That is, can we do away with this mixed precision paradigm? And the answer to that question is yes. And let's look at how we approach this particular question. So to understand what's going wrong with pure 16-bit training, let's look at how a data flows through a graph in a pure 16-bit training regime. In a pure 16-bit training regime, your weights are all 16 bits. During your forward graph execution, you will create activations that are in 16 bits. Then during your backward propagation, you'll create your gradients in 16 bits. And finally, during your optimizer steps, you'll update your weights, and all of those things are also in 16 bits. If we look at what's happening within the compute units, during any of these phase executions, you are taking two 16-bit values. You are accumulating these results in a higher precision. And because these values need to exist in memory at 16-bit precision, you will write these values back at a lower precision using nearest neighbor rounding. And this is what you generally see in current existing low precision training hardware. I would like to argue that the primary source of issues that you see with low precision training and the poor accuracy that you see with low precision training is because of this nearest neighbor rounding approach. Now, before we get into why nearest neighbor rounding approach is bad, let's take a look at a concrete example and see the impact of pure 16-bit training with nearest neighbor rounding from an accuracy point of view. What you see on the y-axis here is accuracy, and what you see on the x-axis here is iteration. And in this case, we are training a very simple BERT MNLI model. What you see is that if I compare 32-bit training graph, which is in blue, with a pure 16-bit training graph, again, no mixed precision training, in green, I see a 16% drop in accuracy. And no amount of hyperparameter tuning allows you to sort of close that gap. So this effectively renders the application useless. No one would ever trade off so much accuracy for any kind of benefit. So let's try to understand why nearest neighbor rounding is bad. To understand that, let's look at how gradient updates impact the optimizer step. In an optimizer step, you consume a batch, a mini batch, you calculate the gradient for that mini batch. Say if it's your simple stochastic gradient descent, you will multiply that with some kind of learning rate, and then you'll update your weight values. And before you write the updated weight values into your memory, you will do nearest neighbor rounding. Now let's try to understand visually what's happening. Your lower precision training regime has sort of developed certain quantization buckets within which your weights need to live. When your mini batch comes in and you have your updated gradient values, you are trying to sort of shift these weight values from the quantization bins that you currently have to a different location. If these weight values are small, these values will never get knocked into the next or the previous bin. And effectively, after rounding, you will come back to the same location where you left off. This kind of leads to a model halting behavior where your certain weights can get always stuck at a particular bin that you had achieved. We hypothesize that this is the issue, or this is the main reason why pure low precision training with nearest neighbor rounding does not work. Now, this hypothesis is not just an intuition. We have a theoretical sketch that sort of proves that this is actually the reason for lower accuracy. But I won't get into the theoretical proof, and I can point you to the paper later on, which sort of talks about this proof. So the question becomes, how do you solve this problem? Now, there are a couple of different methods that we can use to solve this problem. The first approach is stochastic rounding. In case of stochastic rounding, you do nearest neighbor rounding with a high probability, but with a certain amount of probability, every now and then you would kick your value to the next quantization bin. Either it can be higher or lower depending on what your update was. And effectively what that means is that over time, the loss of information is no longer as severe as it was previously. And what that means is that the final values that you end up with are closer to the 32-bit values that you had previously seen. Another way of sort of accounting for this halting behavior is using Kahan summation, which is a way to say we do some amount of bookkeeping. In case of Kahan summation, what we do is that after rounding, we estimate the error that we have seen and sort of note this error down in a 16-bit memory. During your next weight update, you account for this error. And what that means is that because you're always doing this bookkeeping, accounting for the errors that you're accumulating, you are able to mimic the 32-bit training process. Note, the bookkeeping that you are doing is also in 16-bit, so you can still get away with just pure 16-bit hardware in sort of doing low precision training with Kahan summation. Now let's look at how these two techniques impact accuracy. In this case, we are measuring accuracy for 3 different kinds of application across 3 different domains. For each of these domains, we have a notion of accuracy on the y-axis and the epochs or iterations on the x-axis. We have the pure 32-bit training in blue, the pure 16-bit training with nearest neighbor rounding in green, and pure 16-bit training with stochastic rounding or Kahan summation in orange and red. And for all these 3 graphs, what you see is that both stochastic rounding and Kahan summation can enable you to achieve pure 16-bit training without having to see the accuracy losses that you were previously seeing. Now the question becomes, which method is better? Both methods have the trade-off. Stochastic rounding requires an additional cycles that you spend in your compute units to do stochastic rounding. Kahan summation requires you to use more memory in order to do 16-bit training than what pure 16-bit training does. But both of them achieve their objectives of allowing your hardware to get away with only 16-bit compute units. So I talked about the innovations at the architecture level and the algorithms level and how they complement each other to create a highly efficient system. Now let's look at how we are using this system to create applications or sort of get performance on existing applications that were previously unheard of. Specifically, I'll talk about 2 different regimes. One is the computer vision application domain and one is the natural language processing application domain. So let's start with the computer vision application domain. In case of computer vision, what we are observing is that our image capturing systems are getting better and better by the day. Specifically, the kind of resolutions that we care about is actually increasing every day. In case of medical imaging and astronomy, we are looking at images of the size of 50K cross 50K. In case of autonomous driving, we are looking at images of the size of 4K cross 4K. However, a lot of existing deep learning algorithms are still stuck at lower resolution images. And part of the reason for that is because as you move to higher resolution images, the amount of activations required that you need to store in a convolutional neural network significantly increases and you quickly run out of memory on a GPU. One of the ways to kind of deal with this problem is using patches or tiles. Now, you can, in theory, tile these sort of images and feed it into a GPU and do some kind of sort of complex management of your memory. However, when you sort of start tiling this and start running these convolutional neural network algorithms on each tile specifically, you lose out on the natural spatial information that exists in these images. And if you have a hardware architecture that allows you to actually run these at their full resolution, you would see that you can actually push and get much better accuracy than what you had seen previously. And Samba Nova's hardware-software sort of architecture with the compiler allows one to do this. And these numbers that you are seeing is actually a published paper with Argonne National Lab. These issues with sort of patching and tiling not only exist in astronomy, even in medical imaging, where you sort of deal with these large images, you see this kind of an issue. Right now, to sidestep this issue on a GPU, what you do is that you do some kind of convolution neural algorithms. In this case, this is around cancer cell research. You look at each patch of an image, you understand whether these cells are good or bad, and then do some kind of majority voting on them. But majority voting is noisy. The smaller your sort of patch, the noisier it gets. So again, if you have a hardware-software architecture that allows you to operate on larger and larger patches, you can do away with this noise, and you can get much better accuracy. And this is also an active work with one of our collaborators. Yeah. Next, I want to talk about some of the innovations that our architecture has helped us do in the natural language processing domain. A lot of you would be using some kind of natural language processing application on your day-to-day life. These would be your smart home applications with your Siri, your Alexa devices, or OK Google devices. In all of these cases, what you're trying to do is get an application that is very latency sensitive. As soon as you give a certain command, you are able to get a response quickly. What is unique about these applications is that they rely on the left-hand side of the curve of that Goldilocks zone curve that we talked about previously. These generally use some kind of deeper, skinnier models or a tiny BERT model, and sometimes have shorter sequence lengths. And what we have observed is that for these kind of specialized models, if we use our architecture and if we use Dataflow computation, we are able to get anywhere from 3.4x to 11x speed up, depending on the kind of benchmarks that we are running on. For a more complex benchmark like BERT, large running squad, so now you are not trading off these sequence lengths or sort of making the model smaller. Using this Dataflow compute, using this compiler and this Dataflow compute architecture that we have, we can see anywhere between 2x to 4x increase in throughput when compared to A100 models. Next, we are also using these architectures to sort of scale out. We are very much aligned with the neural language scaling laws that we have seen, and we are building applications with billions and billions of parameters. However, what we observe is that the unique software ecosystem that we have created, anybody can sort of train these extremely large language models. And our customers are already training these extremely large language models without having to be systems engineering experts in trying to understand model parallelism, tensor parallelism, balancing the compute and communication trade-offs. And they are not only training these large language models, but turning them into interesting solutions that power their enterprise AI applications. We have also been inherently training these large language models internally and comparing whatever we get with community checkpoints, and we are seeing that we are actually quite better than checkpoints released by companies like Meta or other things that are available on Hugging Face. All right, so that's all that I had for you today. I wanted to sort of sample across different layers of our stack and talk about the different things that we are doing. Hopefully you find that interesting. I can take a couple of questions now, I guess.
Yes, you do.
But I'll be available here for lunch and also the QA session.
If you have questions over that.
Use Dataflow computation. We are able to get anywhere from 3.4x to 11x speed up, depending on the kind of benchmarks that we are running on. For a more complex benchmark like BERT, large running squad, so now we are not trading off these sequence lengths or sort of making the model smaller. Using this Dataflow compute, using this compiler and this Dataflow compute architecture that we have, we can. So from a time to accuracy point of view, you are actually faster, right? Because you can do more compute if you're in a pure 16-bit regime, right? You also save from a DRAM bandwidth point of view because you are loading in less tensors. Stochastic rounding adds a little bit, but it's not enough. It's a single cycle that you will see in each compute, right? And then if you sort of parallelize your matrix vector multiplications or matrix multiplication enough, you can always hide all of those latencies.
Thanks so much.
Yeah, thank you.